In this video, we're going to take a few minutes just to introduce a new coordinate system called the spherical coordinate system. And again, the word spherical should conjure up some images in your mind about a sphere. And maybe now we're going to come up with a coordinate system that makes it easier to describe spherical objects, right? As opposed to rectangular or cylindrical objects. So let's see how all these coordinate systems relate. So we'll start with our original x, y, z space. And I'll make this a little bigger, that way I can put stuff here. Right, so we know, let's say x, y, and z. And again, I'm just trying to plot a point in a relatively easy part of the coordinate system, right? So that we can see things more clearly. So you have your x, your y, and then of course you have your z, so parallel to the z-axis, all right? So that's your point there. Oh, let me write it like this. So just x, y, z. And then we know about the cylindrical coordinate system, where instead of using x and y, we use an r, a theta, and the same z. So again, maybe I could make that dotted as well. So green and white. So then we know that this ordered triple can be expressed in terms of r, theta, z. All right. Now, here's what the spherical coordinate system does. In both the rectangular and the cylindrical, if you think of these like either solid or dotted lines that I've drawn, neither of them present the direct way from getting from the origin to my point. Direct meaning, okay, like in terms of x, y, and z, I have to walk along the x-axis in this direction, and then walk parallel to the y-axis in this direction, and then go up z units again to get to that point. So that was not the shortest path by any means. The cylindrical coordinate system, it improves on it just a little bit. It goes along this diagonal, right? And then it goes up, but still not the most direct way. Well, the most direct way to get from the origin to this point is by doing this. There you go, right? Cut out all the middle stuff. And then once we do this, we have a line segment, and that blue, the distance of this blue is, we choose the letter rho, so a Greek letter rho. But once I do that, if I look at theta and rho that I have here, these are two numbers, two angles that we have. Actually, theta is an angle, rho is a distance. These two alone, they don't define that point P, because I could essentially, and I'll draw this and erase this, but I could almost, I would say, on some kind of an arc, go further away. It looks like I'm going further away from my z-axis and still have the same rho and theta values. So that doesn't, not yet, uniquely define that point. So I need something else to uniquely define that point. And what is used is another angle. And it's the angle that the blue line segment makes with the positive z-axis. So this angle right here is another angle that we use, and that's called phi, right? And the standard, now, what I would say with the cylindrical coordinate system, sometimes different symbols are used, and sometimes a different order is used in terms of the order triple. But the order that we will use, it's going to be rho. So here's another way of doing it. So that distance, rho, and then your theta, right? So theta, and then your phi. Now, the phi could be written there. This is var phi, and then this is regular phi. If you want to get really picky with your Greek things, you can use either one of these. But this is our phi, right? And these are the three spherical variables that can be used to define a point. Now, let me just specify some things about these variables, because these are less known than the previous variables that we've been using. Because rho is a distance from the origin to our point, then our rho is going to be greater than or equal to 0. That's good. Theta, again, is that sort of that angular measure. You can almost think of it as it gives us the degree to which points are rotated around the z-axis, right? So again, the standard requirement for theta is 0 to 2 pi. Now you can argue, well, since I've already included 0, do I need to include 2 pi because it represents the same point basically? You're back to where you started. Here I'm just going to use all my inequalities as being closed inequalities. So that's again the standard range for theta. And then for phi, what phi is, the smaller phi is, the closer your point is to being on the z-axis. And if phi, for instance, is 90 degrees, then your point is now in the xy plane. And then if your phi, let's say, is pi, 180 degrees, so that means you'd be below the xy plane, actually pointing down on the negative z-axis, like this. So our phi, so in fact, let me write this here also in blue. Our phi ranges from, so a phi of 0 means that your point would be on the z-axis. And then the largest value that phi can take on in this coordinate system is pi, right? So and that's where you're on the negative z-axis. So if phi is 0, you're on the positive z-axis. If phi is pi, then you're on the negative z-axis. So that's our range for phi. So it's 0 to pi. Right? And I'll just say a little bit more again. I think it's easier to visualize these two variables, but the phi, if we kind of split it up and say, well, what happens if phi is between, or strictly between, actually we can put the inequalities there, 0 to pi over 2. This means that your point is above the xy plane, right? And if your phi is then between pi over 2 and, I guess technically, let me take this one off. There we go, right? And then if your phi is greater than pi over 2 but less than or equal to pi, then your point is below the xy plane. Right? So 2 angles and 1 distance, and those are the variables that define the spherical coordinate system. Now, we know relationships between x, y, z and r, theta, z. It would be nice to get relationships between x, y, z and rho, theta, z. So let's do just a little bit of geometry here. Now, because my positive z-axis and then this, my dotted line here going up to the point from the xy plane, because those are parallel, it's a little hard to see, but there is a 90-degree angle right here. Right, there's a 90-degree angle right there, again, because it's parallel to the z-axis. And because the z-axis is normal or perpendicular to the xy plane, any line that is parallel to the z-axis will also be perpendicular to the xy plane. Little hard to draw. And then you can use a little bit of geometry to explain, or trig, I should say, to explain why this angle here also has to be phi, right? Because these are complementary angles, right? They all, because of the right triangle here, you can see that this angle right here has to be the same as our phi. So we have this right triangle where we know the hypotenuse, the length of that is rho. We know one of the interior angles, and we also know another length right here, which is the opposite to my phi angle right here. So we can make use of another right triangle and see if we can come up with a relationship between x, y, z, and rho, theta, phi. So but what I'm going to do is I'm going to use the cylindrical coordinate system kind of as the middleman. And the reason why is because the cylindrical coordinate system and the spherical coordinate system, they use the same theta, right? So it seems to make sense that if I know how to get from the white to the green, maybe the green can then help me to get to the blue, and then we'll see what the relationship is. All right, so let's write then what we know in terms of going from going like x equations in terms of r and theta, right? So remember that x is r cosine theta, and then y is r sine theta, and then we know that z is z, right? That's a tough equation to come up with right there, right? Z equals z. Now let's see what does my triangle here that has a blue side, a green side, and a white side, what does that tell me? Well, if we let's use the fact that, again, remember, rho is your hypotenuse. We have this angle phi here, and then r is opposite to the angle phi. So this tells me that the sine of phi is r divided by rho. So it's r divided by rho, which is nice now because what I can do, anything that has an r, if I can solve this equation for r, which I think we all can, we can get that r is rho sine of phi. Then that gives me a way to express x in terms of rho and phi, and also y in terms of rho and phi, because I can basically just replace the r, these r's, with rho sine of phi. So that's helpful. And what we also need is a relationship for z. Well, what is z? In the rectangular coordinate system, z is this side right here, the length of that side. And that is the adjacent side to my angle phi. So let's write that down. So that means the cosine of phi is, what did that be? So that would be z over rho. So z over rho. Solve this for, if we solve this for z, we get that z is rho cosine of phi. All right. So now let's put this all together, and here are the equations that now give us the relationship between x, y, z, and rho, theta, phi. So the x equation is r, which is rho sine of phi times the cosine of theta, right? And then y, in fact, let me go down. So y is r, same thing, rho sine of phi, but now sine of theta. And then z, write down the z equation over here, it's rho cosine of phi. And there you go. So those are our relationships between all the three coordinate systems. And usually, you have nice little formula sheets that show all the conversions. Because remember, the goal here, even though you're learning about these new coordinate systems, and we could explore them a lot more deeply, The goal is to use these new coordinate systems to simplify more challenging multiple integrals, whether it's polar in the 2D case, we've seen the cylindrical in the 3D case, and in the next video, we're going to see how the spherical coordinate system can help us simplify certain triple integrals. And what we will do in the next, at the start of the next video, is talk about the Jacobian for this. And it's going to look a bit scary, so I would say brace yourself, and I'll see you in that next video.